The goal of this project was to create a mechanism capable of moving the endpoint of a surgical tool through a defined three-dimensional path. The final mechanism consists of three main parts: a rotating base, a lead screw assembly, and a rack and pinion assembly. By using three independent mechanisms for three separate dimensions, any sort of failure would mean isolating the failing mechanism and fixing it, rather than an entire redesign.
Motion in the x-axis was achieved by using a lead screw assembly with 3D printed nuts. The lead screw is held up by two 3D printed supports. The acrylic housing around it serves as a support for the plate above it. The plate is fixed to the nuts, preventing them from rotating along with the lead screw, causing them to translate solely in the x-axis when the lead screw spins and moves the mechanism in and out. A pulley system connects the motor to the lead screw, spinning the lead screw as the motor turns. A double-sided rack driven by two pinion gears provides motion in the y-axis. To prevent the rack from wobbling outwards as it is traveling up or down, a housing made from three separate layers of acrylic pieces held together by screws were used. This mechanism was mounted onto the edge of the lead screw platform using L-brackets. The left pinion gear is directly coupled to the motor, which rests behind the rack and pinion housing with a 3D printed shaft. The right pinion gear freely rotates, transmitting the power from the left pinion gear to the other side of the rack. This two pinion gear configuration prevents the rack from jamming. The rotating base was initially a Lazy Susan S device, with the main source of motion stemming from a worm gear. However, structural inadequacies altered the axis of rotation, preventing the worm gear from properly transmitting the motion and turning the upper plate. This illustrates why three independent mechanisms was a superb design choice, as the design was eventually given up on and a new, atypical planetary gear was created using much of the old parts. The planetary gear is not a true planetary gear. It consists of only a sun gear and an annular gear, both laser cut from acrylic. The annular gear sits just below the bottom of the top plate and top of the side supports. It is bolted to the four aluminum seat brackets, which are in turn bolted to the base plate. A pocket for the motor was milled through the top of the upper plate half an inch down, and the motor shaft extrudes through the top plate entirely. An aluminum interface was press-fit in the center of the sun gear. The other side of the interface is connected to the motor shaft with a lead screw. As the motor turns, the sun gear rotates, following the annular gear. Because the supports are grooved and lined with many bearing balls, friction as the top plate rotates is minimum, so that as the sun gear follows the path of the annular gear, the top plate rotates as well. Here we see the arthroscope following path 2, which demonstrates the range of motion. A ball and socket joint connected to the rack and pinion allows the machine to grip the end of the tool with the help of a set screw. The lead screw pushes the arthroscope in and out while the rack and pinion moves it up and down. The new and improved planetary gear mechanism gives us a more stable and reliable turning motion and allows the tool to constantly achieve its range of motion and follow the intended path.